Hello, and welcome to Lab 8, Tsunamis. What is a tsunami? Tsunamis are extremely fast-moving waves generated by major ocean events. In the deep ocean, tsunamis can move as fast as a jet plane or greater than speeds of 500 miles per hour. Tsunamis can cross entire oceans in less than a day and persist for many hours. How are tsunamis generated? A tsunami can be triggered by a submarine landslide, surface landslides, volcanic eruptions, and underwater earthquakes. In all scenarios, abrupt and large volumes of earth and debris rapidly displace ocean waters. Plate tectonics and earthquakes. Plate tectonics relates to the structure of Earth's crust and the large-scale processes that take place within it. Earth's crust is divided into tectonic plates which move slowly over the underlying mantle. In areas where oceanic plates subduct beneath continental plates, earthquakes can produce large-scale displacements of the sea floor. The uplift of the ocean floor can generate tsunamis. Thus, earthquakes are one of the greatest tsunami risk hazards. Subduction zones. A subduction zone is a convergent boundary where one plate is forced down into the mantle beneath another plate. As illustrated in the figure, when an oceanic plate subducts beneath a continental plate, a deep ocean trench is created. Sometimes areas within the trench become locked, and the sudden release is known as an earthquake. The point on the surface vertically above the focus of the earthquake is called the epicenter. When an earthquake occurs in an ocean trench, a fast-moving deep-water tsunami can be generated when there is a large upward displacement of the seafloor. The seafloor imparts energy into the water column, and underground seismic waves are transmitted into the water. The following animation demonstrates how an earthquake can be produced along a subduction zone, as well as the subsequent release of a tsunami. The deadliest tsunami in recorded history. On December 26, 2004, at approximately 8 a.m. local time, a massive undersea earthquake of magnitude approximately 9.0 occurred offshore Sumatra, Indonesia, and created the greatest natural disaster in recorded history. Within the subduction zone, the India and Burma plates had become stuck together. Along the deep ocean trench, the two plates suddenly broke free and uplifted the seafloor more than 2 meters. However, rather than rupturing all at once, the upward displacement migrated north along the fault trench at speeds of greater than 2 kilometers per second, spanning a total distance of 1,500 kilometers. The Sumatra 2004 event ruptured the greatest fault length in recorded history. The following animated simulation illustrates the event. The displacement of the ocean floor thrust the water column upwards as it migrated north. The giant push of water generated a series of tsunami waves. The resulting tsunami averaged in speed of 190 meters per second or 425 miles an hour. The following map delineates the tsunami distances traveled in 1-hour increments. In your lab assignment, you will create a similar map. By calculating the tsunami speed, you will mark distances traveled by drawing circles on your map. Additionally, you'll work with time zones to determine local arrival times, which we will discuss later. Next, you will view a wave animation that demonstrates the propagation of the Sumatra tsunami. Sumatra was first struck by the wave approximately 25 minutes after the event. Thailand, roughly 2 hours later. Many other countries were consecutively impacted by tsunami waves. The tsunami reached East Africa coast nearly 8 to 10 hours later. Sea withdrawal and the approaching tsunami. Prior to the tsunami's arrival, there was a major withdrawal of the sea. Many onlookers were intrigued by this unusual sight until they saw the oncoming tsunami. Unfortunately, these pictures now represent a warning to us all that a tsunami wave is coming. Sadly, many people were caught unaware of the impending danger. The tsunami surged at 15 to 30 meters, or ranged 50 to 100 feet, and the massive influx of ocean water persisted for hours. Moreover, multiple tsunamis impacted the coastline, and the seas moved inland relentlessly. As the sea level of the ocean rose, areas along the coastline were inundated. Once the seas finally retreated, the contents of debris flows could be seen. Unfortunately, entire communities were lost. The following slides show before and after images of the tsunami impact. Here is the before image for Lombok, Indonesia. And here is the after image. Here is the before image for Phi Phi Village in Tonsai Bay, Thailand, which was the center for many shops, restaurants, and bungalows. And then seen afterwards. Sadly, on December 26, 2004, over the course of a day, more than 200,000 people lost their lives. The loss of life was felt throughout the Indian Ocean region. Additionally, material losses were estimated at $10 billion. Your lab calculations. Next, we will focus on your lab assignment calculations. You will begin by estimating the average tsunami speed by using the following formula. C equals the square root of G times D, whereas C, or celerity, is the tsunami speed measured in meters per second, gravity of 9.8 meters per second squared, and D for ocean depth measured in meters. In your calculations, your lab instructs you to use an average of ocean depth for D of 3,730 meters. Remember, because you're calculating speed, your final answer should be in meters per second. Next, you will calculate distances traveled by the tsunami using the following formula. D equals V times T. In this case, D equals distance, measured in meters, V is the speed of the tsunami, measured in meters per second, and T is time, measured in seconds. To complete your table, you will repeat these calculations for each of the following time spans of 2, 4, 6, 8, 10, and 12 hours. To begin the table, you will first convert the number of hours into seconds using the conversion provided below. You will then compute your distances. However, notice that the distance column asks for your answers to be in kilometers. Use the conversion provided below to change the answer that you calculated earlier from meters to second to kilometers per second. Plotting your distance circles. Using the distance calculations from your table and the scale bar given on the map, you will plot distance circles to indicate the location of the tsunami 2, 4, 6, 8, 10, and 12 hours after the earthquake. These circles will be centered around the epicenter as labeled by the red star. Also, you will label each circle with the number of hours accordingly. How to draw the first 2-hour distance circle. First, you will look to your table. You should have calculated that your tsunami traveled 1,375 kilometers in 2 hours. Next, utilizing the map scale bar, as seen here, you'll determine the size of your 2-hour circle. The map scale ranges from 0 to 10,000 kilometers and is divided into 2,000 kilometer segments. Then you'll estimate the size of your 2-hour circle. Next, you'll align your 2-hour circle over the epicenter, and finally, you'll label it. You will then repeat this process for creating additional circles for 4, 6, 8, 10, and 12 hours. Plotting your tide gauges. Finally, plot the location of the 2 tide gauges that monitored the tsunami during the event. Your lab provides specific locations for the buoys. Station A, the Hanamaru buoy, is located at 6.5 degrees north, 73 degrees east. And Station B, the Lamu buoy, is located at 2.5 degrees south, 40 degrees east. Try and be precise as possible in plotting the locations of your tide gauges. You will utilize your tsunami distance calculations to estimate the tide gauge arrival times of the tsunami. Time zones. Additionally, you'll need to work with time zones. As the tsunami traversed the Indian Ocean, it crossed time zones. Each time zone represents a 1-hour time change. For example, as you move west from the epicenter in Sumatra, then 1 hour is subtracted with each time zone. Conversely, as you move east from Africa towards Sumatra, 1 hour is added with each time zone. When you answer your questions in your lab related to tsunami arrival times, make sure you answer in terms of local time. Tide gauge charts. Finally, you will utilize the recorded tide charts for the Hanamaru and Lamu tide gauges. Each tide chart reflects the measured water levels, measured in centimeters along the y-axis, and time measured in hours along the x-axis. Both charts show 2 distinct signals. A main continuous signal that is thick with a long period representing the ocean tide, and a shorter period signal overlaying the main tide signal representing the tsunami. Next, you will determine actual versus predicted tsunami arrival times, as well as calculate period and amplitude. First, we will measure the period of the ocean tide. Period is the time it takes for one wavelength to pass a fixed point. By measuring the time of the wavelength, you can determine the period. At the Hanamaru tide gauge, period, or T, is approximately 14 hours. Amplitude. First, we'll measure the amplitude for the ocean tide. First, the mean sea level is defined by 0 elevation. Next, measure the distance above the mean sea level. Again, at the Hanamaru tide gauge, amplitude is approximately 50 centimeters for the ocean tide. Arrival times. The actual tsunami arrival time is determined by the tide gauge. Draw a line at the point that shows the actual arrival time of the tsunami signal. Next, you will plot your predicted tsunami arrival time based on your previous calculations. To plot your predicted tsunami arrival time at Station A, the Hanamaru tide gauge, estimate the time using your calculated distance circles. Station A should lie approximately on your 4-hour circle, as seen here, or 4 hours after the event. So if the event occurred at 8 a.m. Sumatra time, then your predicted tsunami arrival time at the Hanamaru buoy should be 4 hours later, or 12 p.m. However, this is Sumatra time, and you need to convert to the Hanamaru tide gauge local time. Time conversion. When you convert to the Hanamaru tide gauge local time, you begin from Sumatra time and count backwards. However, Notice that the time zone bends around Sumatra. Counting time zones in this case, from Sumatra to the Hanamaru buoy, the total time difference is 2 hours. Now plot your predicted arrival time. If the tsunami reached the Hanamaru buoy at 12 p.m. Sumatra time, then your predicted arrival time is 2 hours less, or 10 a.m. local time. Draw a line at the time that you predicted. Next, we're moving to Station B, the Lamu buoy. In your lab, you will determine the periods and amplitudes for the ocean tide and the tsunami, as well as the actual and predicted tsunami arrival times at Station B, the Lamu tide gauge. Period. Measure the period for the ocean tide. At the Lamu tide gauge, period is approximately 13.5 hours. Next, measure the ocean tide amplitude. At the Lamu tide gauge, amplitude is approximately 140 centimeters. The amplitude of the tsunami signal is measured as displacement above the ocean tide. To measure the tsunami amplitude, begin by tracing a line along the ocean tide. Then locate the largest tsunami signal. This is called max displacement. Finally, measure its amplitude, in this case being approximately 70 centimeters. Arrival times. Next, plot the actual and predicted arrival times for Station B. Draw a line at the point that shows the actual arrival time of the tsunami signal. Next, from your distance calculations, determine and plot your predicted arrival time. Make sure to convert to the Lamu tide gauge local time. Reflection questions. In your lab, you will need to speculate on why the tsunami actual and predicted arrival times differ. In your discussion, you'll want to focus on factors that would affect your calculations. For example, varying coastlines with different slopes and depth, inaccuracies in your map locations, for example, your buoy locations, and inaccuracies in your tsunami travel times. Also, your calculations used a constant ocean depth, while actual ocean depths vary. Additionally, you'll need to discuss differences in the ocean tide and tsunami displacements that change between your tide gauges. For example, you may consider that India's relative distance compared to Africa, or tidal differences based on coastlines. Also, there may be possible differences in the slope of the coastlines, as well as possible errors that you inserted during your calculations. Thank you for attending Lab 8, Tsunamis. Please address your questions to your lab TA.